Hi everyone, welcome to my poster presentation. My name is Jinfang Zheng. I'm a postdoctor from in-lab at University of Nebraska-Lincoln. My projects focus on developing bioinformatics tools and the genome annotation. Today I will introduce a software dbCAN-profiler, automated carbohydrate-active enzyme annotation using knowledge. We we know that carbohydrate-active enzyme is an important type of enzyme with its function on saccharides, and the organism employ enzyme to obtain energy. Hence, it's very important to detect enzyme gene in organism genome. In 2012, we developed a tool dbCAN for automated enzyme annotation based on the genome sequence and protein sequence. However, with the next sequencing technology is widely used in the researches, high throughput reads was sequenced. More and more researchers want to detect the case size, occurrence, and abundance without assembling the reads into genome. Due to the assembly limit such as time and the low sequencing depth. So we are working on dbCAN-profiler, a tool to detect abundance and occurrence of cases from low risk without assembly step. Figure 1 shows the three peptide of dbCAN-profiler. Our peptide starts with 22 standard golden, golden standard genome. Peptide 3 is also called golden standard peptide, which is only used as standard to justify the performance of peptide 1 and peptide 2. Peptide 1 is the assembly-free approach. The golden standard genome was simulated by chemists in order to generate the NGS reads, and then we use BWA to map the reads to the KSI-CDS database, or use diamond to plot X the reads to KSI protein database. Based on the mapping results, we can calculate the abundance and occurrence of the KSI. In the assembly-based approach, we first assemble the reads into genome, and then use dbCAN to predict KSI, and then we also map the reads into the genome to calculate the abundance and the occurrence of the case. We then compare these to the peptide-free results. After we build this, we test the peptide on the sequencing list. First, we compare the running time for assembly-based and assembly-free peptide as shown in the figure 2. We test peptide 1 and peptide 2 on different sequencing depth from 1x to 100x. In a lower depth, the time is almost the same for these two peptides. However, the time of the assembly base is increased with the depth. This shows the assembly fleet will use less computation resources, especially for the high sequencing depth. Second, we compare the ROC curve and F-score for peptide 1 and peptide 2, as shown in figure 3. The left panel shows the assembly fleet method, assembly fleet results, and the right panel shows the assembly-based method. In a low sequencing depth situation, the assembly fleet performance much better than the assembly-based. When the depth is 100x, these two peptides have the same performance. And then we show the details of assembly fleet method in case-size detection. In figure 4, we show abundance and occurrence of the case-size family. The inset when figure shows occurrence of the case-size for peptide 1 and the peptide 3. This shows assembly-free method predicts one false positive case size, while carbohydrate 1 only means 4 case size family in 1x step situation. The distribution of the case size family in shows the assembly results is close to the peptide-free results, except for some cases, such as case size family from GT, and CBM. We then shows the distribution of absolute of abundance change in Figure 4. As shown there, most of assembly absolute change is equal to 0, indicating the same result with Figure 4. Based on current results, we have the following conclusion. As first, assembly-free method has less running time comparing to the assembly-based method. Assembly-based free method has a better F score and AUC than assembly-based method. The estimated abundance of assembly-free is close to the golden standard peptide. That's all for today's presentation. Thank you.